So last week we trained GPT-2 from scratch, which means we pre-trained GPT-2 from scratch using book corpus dataset. So typically we won't do pre-training. So what we do is the corporates like Meta AI do pre-training, they released Llama model. So last month they released Llama 3.2. So we are going to continue the pre-training process of Llama 3.2 1 billion parameter model. There are different variations. So you can use 3 billion or even 7 billion, 70 billion. But we are going to use 1 billion model parameters and we are going to continue the pre-training process. So Llama 3.2 was trained on 9 trillion tokens. So it has a good world knowledge, so we are going to make use of that, but we are going to adapt it to some domain specific data set. In this case we are going to use Tamil subset of Sangraha dataset from A4 bar. Okay, so this is called continual pre-training. So we have already pre-trained model released by open sourced by big corporates like Meta AI, and we are going to continue the pre-training process. That's why it's called continual pre-training on a domain specific data set, but here we are going to take this Tamil subset. We are going to make use of L4 GPU, which has 48 GB of memory, and we will reason why we picked up L4 GPU for demonstration. Since GPT-2 has, and the small version of the GPT-2 has about 124 million parameters, so it was quite easy to pre-train the model on consumer grade GPUs, even on Colab. But 1 billion, a model with 1 billion parameters takes a significant amount of memory. So sometimes, of course, it is possible to pre-train the model on the consumer grade GPU, but it takes a long time. We can continue the pre-training. So what we are going to do is, so even if we have 48 GB of memory, GPU memory, if we go with the naive model, right, with its default configurations like the data type of float 32, it will take, say, for example, 21 GB, 20 to 22 GB of memory per sample. So we are, so we can train the continue, we can do this pre-training with a batch size of 1 or 2. But we know that having a bigger batch size is always better. So let's explore the techniques like parameter efficient fine-tuning techniques. In this week, we are going to make use of LoRA, and also we are going to combine it with quantization so that we can increase the batch size. Okay, let's get started with the typical imports. So we have already used all these functions from the Transformers library and also the datasets. So no need to explain it further, and set up the WNB for experimental tracking. Okay, so we are going to use Sangraha dataset, especially the Tamil subset, even not all the portion of the Tamil subset. So the dataset is really huge. So for this demo, we are going to use only a part of it. So you can download it and you can see that there is a 0.1 million samples. Of course, the sample size is quite large, unlike the previous cases. Each sample size is quite large. And you can see that, as usual, there is a text and also other features, but we just need text because we are going to do only pre-training, and that's a pre-training dataset. So we need to download the model specific tokenizer. So since we are using Llama 3.2 and using the auto tokenizer function, it automatically downloads the suitable tokenizer from the hub. We can simply set the model ID. So it is from Meta AI Llama 3.21b. If you want to download the instruction fine-tuned model, you can also set Llama 3.21b chat or 1b instruct, something like that. Note that the vocab size is 128K. This is really huge because it is a multilingual model. So when you tokenize on all the available data from the internet, we can expect that the vocab size is having a vocab size of 128K is a good one to represent all the language. And moreover, the context length, compared to the previous version of Llama, the current version has a really huge context length 131K, but anyhow we are going to limit it for our demo purpose 2024. So we modify the model max length 2024, and also we set the pair token ID. So typically while you, I mean, it is a usual case for all the models. So you have to always set the pair token, which one is the pair token. So we are just setting the end of sentence token as a pair token. One aspect that we haven't explored so far is, of course, we computed two quantities. One is how much a word is split into tokens. Say I have a sentence that contains some 10 words, then after tokenizing the sentence, the number of tokens might be, 16, or it could be 32, based on the type of tokenizer we use to tokenize the text. So using these two numbers, we can compute the score called as fertility score. For that, I'm going to take one specific example from the data set and count the number of words by white space. And it seems that the sentence has 47 words. Then using this Llama tokenizer, after tokenizing this, we can see that it splits the word into multiple number of tokens so that the sentence now contains 521 tokens. So using these two quantities, we can calculate the ratio, and if you calculate that, the ratio is about 11.08 for this specific example. So this is quite a high score because each word approximately is split into multiple tokens in this case, and an average it is split into 11 tokens. Of course, to compute the actual fertility score, you have to tokenize the entire data set and then take this ratio, then only it will give the actual or the average number of tokens. But anyhow, let's go with it. But we can see that the fertility score is quite high because the tokenizer, typically it is the case for all Indic languages. The fertility score is high, which means each word in the sentence is split into 5 to 6 number of tokens. Okay. So here, since we use Tamil, so even if you don't know Tamil, that's fine. So you can see that the words are well separated by only white space. So there are 47 words in this particular example. Then after tokenizing it, of course, because we are using byte level byte pair encoding, we can't make sense of it. But anyhow, when you decode, it is able to reconstruct the tokens, which means in the original language. So if you count, then I just printed first 47 tokens, but as you know, it contains about 500 plus tokens. So when you really train the model, it is like if you take a sentence and a sentence containing just 47 words, turned into 521 tokens. So even if you pass two sentences, we will quickly reach the context length. Say, for example, if I have another sentence and pack it as a batch, just with two sentences, it occupies the entire context length of the model. Anyhow, for the demo purpose, we are going to stick with this. We are not going to retrain the tokenizer so that, um, we can, if you retrain the tokenizer on this new dataset, we can reduce the fertility score. But anyhow, we are not going to do that. Just for this demonstration purpose, it is more than suffice. Okay, so after tokenizing, yeah, so the typical thing, you just define the tokenizer function and then pass it to the map function. Then you will get the text is converted into input IDs and then attention marks, because the model process the input IDs and it requires just input IDs and attention marks. The usual thing. So we have to pack the sequence. So all the settings that we followed in while training GPT-2, we follow the same here, because continual pre-training is nothing different from pre-training. So I'm just skipping this part. So after doing this stuff of packing the sequence, where we chunk the sequence so that all the samples in the dataset contains 1024 tokens, we just ensure that. Finally, we save the model to the disk, sorry, the dataset to the disk, and then we can load it back. So we loaded it back, and you can see that as expected, the original data set, right? Contain about 0.1 million samples, but after tokenizing and then, packing the sequence, now the number of samples in the data set is quite high, which is 0.4 million. So that is fine, right? Yeah. Again, we split the dataset into train and test splits just to compute the training and validation loss. And yeah, we have to do this data collector. And because we are doing this pre-training, continual pre-training, which is with the CLM objective, we use the same data collector function that we used for GPT-2, and we set MLMs equal to false. Okay, now comes loading the model. Llama 3.21b, is a gated model, meaning that even though it is open sourced, we have to submit the form to get the access to the weights. So in Hugging Face, if you have your account and you go to the Llama 3.2 page, and then there is a form you submit, and within an hour they will grant you an access to download the weights. So you can load the weights and then experiment with the model. Okay. So we need to understand before start training the model. It is very important to understand the details about the model. Like, so here are some important details. As you can see, the number of parameters. Of course, they call it as 1 billion model, but if you count actual number of parameters, it turns out there are about 1.23 billion parameters. And context length, yeah, it's 128K, but it supports 131K. Vocabulary size, as we have seen, it is 128K. And the input it is actually trained on all the, it was actually trained on 9 trillion tokens, which likely contains mostly all the tokens are, from English, but it contains other languages as well. So it officially supports some 6 languages, including Hindi, but not Tamil. So that's why we are going to, continue the pre-training on Tamil subset of Sangraha. So it's a multilingual model. And yes, we can see the model was trained on 9 trillion tokens, and knowledge cutoff is December 2023, which means the model has no knowledge about the events that occurred after December 2023. And as you can see, we can't even train this model from the scratch, because if we really want to train this model, we need 180 GB. But how long we have to run? We have to run 916K hours if we have only one 180 GB. So we need a cluster of 80 GB, 180 GB, and to train models like this. Okay. So as usual, so we have to load the model. For that, we use auto model for Castle LM, and there we are passing the model ID, so which we have set to Llama 3.21b, and also we are setting the path token ID, which is typically the end of sentence token. So once we load the model, with the pre-trained weights. Remember earlier when we train the GPT-2, we load the models so that the model weights are initialized randomly, right? So we use GPT-2 model for LM, but here we use auto model for causal LM, and also using this from pre-trained method so that it loads the pre-trained weights. Yeah, so let's look at the architecture details in the configuration architecture. So once you print the configuration, you can see that the BOS token ID, EOS token ID, and the important quantity is what is the hidden size. So in the MLP layer, the 2048 is the embedding dim, and they are using the same 4 times 2048, which is 8192 as an hidden layer size in the MLP layer. Okay, so the 2048 is in fact the embedding dim. Okay, so all the details, and you can see that they use something called as rotary position encoding instead of absolute position encoding. Okay, of course you may not have heard about all these different types of encoding techniques, but it is fine. Just think about it as a much better embedding position embedding techniques, especially when we have really a big context length. Now we print the model so that we can understand the model architecture. So again, the model is decoder based, and you can see that it has all these features from the transformers. But however, here we are just seeing the embedding layer, which the backup size is 128K, and the embedding dimension is 2048. But there is no position embedding layer, but instead the position information is added in the attention head. You can see that this is the position embedding that is added directly in the attention head. So that's how this is a relative position embedding. So they add it in the attention head. And you can see the rest of the things are all make sense. Of course, it gives group query attention instead of a typical attention. So though we are not going into much details, at least having an understanding about the architecture is helpful. And the MLP layer, of course, you can see that it takes an input embedding of size 2048 and the intermediate hidden layer that contains 8192 neurons. Okay, so all these things are understandable. And finally, in the LM head, we have the input of size 2048 and the output is computed over the entire, the tokens in the vocabulary, so which is 128K in this case. Okay, so now we looked at the model details. Yeah, these are all the things. So it uses a relative position encoding. And let's count the parameter as usual. So if we count the parameters, it turns out that it has 1.23 billion parameters. Okay, so 24 billion, close to. Okay, so now we are really interested in calculating the memory footprint of this model, because if we have 1 billion parameters, even to load the model, not even train, just to load the model into the system, so we should calculate how much memory it really takes. Of course, we are calculating after loading the model just for the demonstration. Okay. Yeah, the model right now uses float 32 4 bytes to store each parameters. And when we say parameters here, it includes mostly learnable parameters, but often you have to keep in mind that when we say parameters, it also includes parameters used for to compute the normalization, like mean and variance. Okay, so we don't calculate gradient for those, but still it is counted as parameters. We need to store them, so we need to assign some memory, though it is very small, but it is good to be aware of that. And since number of parameters is 1.24 billion, and for each parameter we assign 4 bytes, so if you calculate the memory, it turns out that we need at least 5 GB of memory to load this model and store it in the CPU or GPU. And HF provides a direct method. We can call that function, and we can see that we have same numbers with a slight difference because we only counted the learnable parameters, but this function counted all the parameters, including parameters that do not require any gradients. Okay. So the model, just to load the model, we need about 5 GB of memory. But if you really want to pre-train or even to fine-tune the model, or if you just want to train in any type of training except prompting, we need additional memory. As you know, we have the parameters, so we need to compute the gradients for all the parameters. So we can expect that we need additional 5 GB of memory, at least additional 5 GB of memory to store the gradients. But if you use a different optimizers, like typically that is the case, Adam optimizer, which has additional parameters, like they keep track of first order and second order movements. So in that case, we need to store them as well, the past history. So it is like we need 3 times 5 GB of memory if we use Adam. So and moreover, on top of all these, because we are going to train the model on the GPU, we need to download the GPU kernels, which defines the GPU specific functions for all the operations involved in the model training. So based on the type of GPU we use, the amount of memory requires changes a bit from 2 to 4 GB. So if we even think of using a modern GPUs where we need at least 2 GB of memory to load all these kernels. So put together, if we sum up all these, it turns out that we need at least 21 GB of memory, to train the model with a batch of size 1. And of course, if you increase the batch size, it is not like it linearly, the memory requirement will increase linearly. It will decrease because while calculating the memory for a batch of size 1, we calculated the memory for model and also for the GPU kernels. But the moment for the next sample, we don't really need to count the memory for the model and also GPU kernels. So we can think of, say, for example, if we have 20, now it requires 22 GB of memory, but if I load a batch size of 2, just increase the batch size by 1, it will require some 33, or say, for example, 34 GB of memory, not 40 GB. Okay. Okay, so L4 GPU contains our 48 GB of memory. So we use a single node L4 GPU where it has 2 GPU instance and each GPU has 24 GB of memory. So put together we have 48 GB of memory. So which means we can train a model. We can train this model as is without doing any parameter efficient fine tuning techniques or even to reduce the data type. We can train this model in this GPU with a batch of size, say for example 3, because we have 48 GB of memory. But typically we really want to increase the batch size. So in that case, you can increase the batch size by using strategies like gradient accumulation. But remember, when you use gradient accumulation, the training time is traded off appropriately, right? So if you increase the steps, then you have to wait for a long for the training to complete. So that's where the parameter efficient fine tuning techniques comes. Moreover, we really don't want to train all the parameters in the model. So because we are just going to adapt it for a downstream task, and it makes sense to fine tune some of the parameters, but there are a lot of studies as covered in the lecture, but we are going to stick with LoRA, the most commonly used one, LoRA and QLoRA. So here we are going to use LoRA. You take QLoRA as an exercise. Okay.